last class we started talking about what I call the two-way ANOVA. So, we are talking about two factors at multiple levels. The special case is two factors at two levels, we will get into those details, but typically two factors at multiple levels, right. So, the model that we are starting to look at is mu plus tau I, you can call it as alpha I plus beta j plus alpha beta ij plus epsilon ijk. The new term is the interaction term, which is alpha beta, okay. Unlike your one way ANOVA or your RCBD, this allows for interactions, and I told you in a simple case how to estimate interaction. If it is a 2 cross 2 experiments, you look at the basically a plus b plus minus a minus b minus divided by 2, that is both are high, both are low, what is the difference, that is the effect of interactions, and you can separately compute the main effect of each variable, okay. So, now our hypothesis can be on three things, whether main effect A is important, main effect B is significant, or interaction effect is significant. So, those are the three hypotheses one can ask about. Now, the next thing is how do I get estimates of each of these interactions, and of course, what are the assumptions involved. This also comes up with its own assumptions. The assumption of Gaussianity is always there. So, and Eij, the error Eijk is going to be Gaussian normal with 0 comma sigma square, that is the usual assumption we make. So, the following are the assumptions that we are going to make in 2 ANOVA. All observations are independent. So, it is not a time series, okay. It is not dynamic, okay. Your outputs are not dynamic. Remember, that is one of the important factors to keep in mind. So, if you look at, say for instance, you are measuring continuously your let us say brain waves EEG, is it a dynamic data or a steady state? Water level is fixed, you measure using a sensor, will the measurements be always the same as a function of time? Will there not be sensor noise? You understand my question? Level is there, level is fixed in a tank, you are looking at the level using a level measuring device. Will you always get a constant value of 13 or 10 feet? Always? Will there not be fluctuations? Is it a dynamic data or a steady state data? You understand my question? So, you have to be very clear on what is dynamic. So, I have a tank and 10 feet or 10 meter is the height, the level. I measure 10 meter using a sensor. Will the sensor exactly give 10 meters every time? Will there not be fluctuations? Your voltage 230 volt, even if you measure, will it be always 230? Will there not be fluctuations? Is it a dynamic or a steady state data? Dynamic data. What is the difference between dynamic and steady state? Is it based on measurements or based on the system? Is it based on the output or is based on the system? Based on the system, right? Is it based on the signal or system? You call it as a dynamic system or a dynamic signal? Dynamic. So, the level in the tank, is it dynamic? I said it is fixed at 10 meters. So, is it a dynamic system, the level? What you are measuring has fluctuations. See, this is very important to understand. When is linear regression? We learned linear regression. Linear regression, did we consider the aspect of time? Did we consider aspect of time? So, linear regression, where is it applicable? For what kind of data is it applicable? It is data from it is a steady state data or data from a static system, okay. So, but in your least squares you get constant output, is it? For a same value of x, what do you get? Y equals to mx plus e is what I wrote, or y equals to theta x plus noise. The variation in the output is not due to variation, even if you keep x constant, y varies. Why? Because of the noise. even though the output has to be steady or static, since you are measuring a steady state system, it should be, the output should be static, but there is variations because of noise. It is not because the system is dynamic. I have told you this linear regression many a times. You look at all pipelines, be it gas, be it water networks, F1, so flow in different pipelines are fixed, constant flows, but if you measure, will it give you exact same time every reading, every time the same reading? Noise in measurements. So your flow values will not even exactly match, there will be fluctuations. Does it mean that the system is dynamic? The system is steady, the output is varying just because of noise in your measurements or fluctuations. It is steady state system. Okay. So here as well we are assuming the system to be static. So EEG now, is it a steady state or a dynamic? Is it you are measuring from a steady state system or a dynamic system? Your EEG waves. You are all biomedical engineers. EEG waves is measured from which system? CNS, central nervous system. Is it steady or dynamic? Why is it? How do you observe, how do you say it is dynamic from the measurements you make? You are measuring alpha, beta, theta, or you are measuring generally the EEG waveforms. How do you say it is dynamic? Looked at EEG, right? How many, what do we use to collect EEG? How do you collect EEG data? Electrodes. Why do you place so many electrodes? Spatial. Is it only spatial? Yes, spatial is important. So there is parietal, occipital, prefrontal, frontal, but what else is there? Is it only spatially varying? Your signals does not transfer from one location to another, so it is temporally as well varying. So it is a spatio-temporal dynamic system in both spatial and temporal, most complicated. It has both spatial variations as well as dynamic. So prefrontal does a certain job, is responsible for certain activity like decision making. The signal generates here but transfers all the way up to the other. The same way occipital has some functionality, major functionality. So it triggers, the signal triggers there, but it transfers to, information transfers to other parts of the brain as well. So in a sense it is a spatio-temporal system with time varying. So imagine our central nervous system, if it is static, everybody will be like a vegetable, right? Basically nothing, no response for dynamic variations, as input is consistent, continuously varying, and even if the input is constant, even in this place, if the external input is constant, is your brain at one location focused? Is it doing only one activity? No, right? So this is a highly dynamic system. Okay. So biomedical signals, if you measure from body, then it will be difficult. You have to make sure what you are looking at. Are you looking at steady state aspect or dynamic aspect? This particular whatever we have learned so far, is only for capturing the static aspect, not the dynamic aspect. So that is why we actually, that does not mean that we cannot do anything with these methods in biomedical engineering. It has lot of applications, we average out. So remember, we say I am not interested in dynamic variation of the heart rate. What am I interested in is an average number for beats per minute. I am not interested in measuring continuous blood pressure. Your continuous blood pressure can never be within a short range and 8 to 120, it will be fluctuating. But what am I interested? On a average values. Okay. So that is where this becomes important. We try to make the system simpler by reducing the dynamic nature or neglecting the dynamic nature and averaging it out to come up with simple numbers that represent a meaningful number, that gives a meaningful number. Huh? You have to, so if you want to think about, so you, you have to know something about the system. It cannot be blind. If you just give me a data and then say whether it is static or dynamic without telling me what it is, it will be as difficult, it cannot be accurate. You have to know something about the system. You are talking about the dynamic nature of the system, right? Your signal is observed from the system. So the system is responsible. So you always talk about dynamic system or not. Even if I say I give me a signal and ask me whether it is time series and dependency is there or independency is there, the first question is where is the data collected from, right? The source is very important. And of course you can do lot of correlation analysis, etc., auto correlations to understand whether there is relationship or not. But keeping aside, the most important thing is to know about the system, not just the measurement. You need to know about the system, right? So that is why this assumption, when independency and static, or you are looking at Yijk are independent, what do I mean by that is when you conduct experiments, you have to be very sure that when you are using ANOVA or when you are using two-way ANOVA or one-way ANOVA or whatever it is, your one measurement is not influencing the other. That means I take a reading from subject A, give a dosage level medicine, and I am observing the, let us say, average what I say, toxicity limits or whatever in the body, right. That will be, if I measure it continuously, the system is dynamic, the body is dynamic, it will actually the toxicity levels will go down as a function of time. What do? I come up with some average number. Remember, that is where you are making it static. If I measure continuously and looking at continuously, it will be a dynamic nature, there will be always fluctuations among people, right. Even for the same person doing today and tomorrow, it will be not the same, the pattern may remain the same, but there will be fluctuations. What do I do is a single number, right. The simplest thing is do an exercise, normal versus exercise. Suppose you do a cardiac exercise, you will have an average heartbeat during cardio which will more or less be same throughout for different today, tomorrow, etc. But will the profile be same? Will the fluctuations be same? You may have sometimes hit 180, then 160, 150, and then, but on an average, if you do a cardio, I know 160 is what my level is, and for another person it may be lower or higher. So your resting cardiac every day will not be, if you measure it continuously in the morning, it will not give you the same number. But if you average it out and then look across days, like for a month, you will say, hey, my resting heart is somewhere around 70 beats per minute. Now you have made it to static, you have taken the element of dynamic nature by averaging. And what I am saying Yijk is independent is, if I am comparing the resting heartbeat of people X versus somebody else Y, they are independent. That is what Yijk independent means. Okay. So you have to be very clear, we are all dealing with static systems or steady state measurements. Okay. Either the system itself is static or you derive metrics so that you do away with the dynamic nature and represent the system in terms of steady state measurements. You understand? Either the system itself is static, which in biomedical is never the case, okay, but you derive numbers so that the system, you represent the behavior of the system using steady state quantities like resting heart rate, average resting heart rate. More or less the dynamics is washed out because you have taken averages. Clear? That is the way this methodology becomes important to biomedical, because otherwise our body as such is completely a dynamic system, that has to be kept in mind. Okay, we only average it out to remove the dynamic nature, reduce the dynamic nature of the system. Okay. So the first thing is all observations are independent. At least now I hope you understand what is independent, what is static versus dynamic. The moment I say dynamic, Yij will be dependent, it will be a function of, in EEG it is a function of time, it is a function of spatial locations. Okay. Same with, if I start measuring PQRS as such, it will be a function of time. Understood? Okay. And the second observation is additivity. This is something which you have been doing it, we did not mention it explicitly. All effects are additive in nature, that is the row effect, we have a model that is row effect plus column effect plus interaction. Nobody told that it should be additive, it could be very well multiplicative, it could be square whatever. What we have taken as a simple additive relationship in this kind of approaches, okay. And of course the last one, noise is IID 0 mean variance sigma square because of the central limit theorem, okay. So these are the assumptions mainly in two-way ANOVA, which is same as that of ANOVA as well.